We finished up chapter 32, and our first topic is going to be the magnetic force on a moving charge. So first of all, the force, in order for there to be a force, the charge has to be moving. And even more than that, if the charge is moving, as in this picture here, completely parallel to the magnetic field, there is no force. And so here's a case where basically there's a little bit of a direction, so the actual particle has a component, this much component of velocity that's perpendicular to the B field, and there is a force. And you'll note here that the force, F, is perpendicular to the plane that the B field and the velocity make. And we find that the biggest force you can have is when the velocity is completely 90 degrees to the B field. Okay? And so in equation form, how we get this is this thing here is called the cross product. And basically what the cross product means is that we have this guy here. This is the magnitude of our force. This is the charge of the particle, the velocity, and the B field, and the alpha is the angle between the velocity and the B field. Right, and we see that this gives us exactly what we want. When the angle is 0, sine theta is 0, and when the angle is 90, sine is 1. So that's exactly what we want. So that's the magnitude. The direction we use, the right hand rule. Knight uses this situation where you take your right hand, you make it kind of into a little x, y, z coordinate axis. Your thumb is with the velocity, your fingers with the B field, and your pointer finger, and then your middle finger is the force. Now what I'm going to use, because this I think will work better in the lecture hall, is a similar version, but it's called the flat right hand rule. It's almost the same thing. Your thumb is the velocity, your fingers are the B field, so that's consistent, but then it's your palm that shows the direction of the force. So it's very similar to this one here, it's just your hand is flat instead of with your middle finger sticking up. All right, and so if we look at the cases here, so this case over here is that special case we were talking about here, where when the velocity and the B field are in the same direction, the force is 0. This case over here, if you look at it, if my thumb goes with the velocity, my fingers go with the B field, my palm points into the page. If I do this case over here, this bottom case, if my thumb is with the velocity, my fingers point into the page with the blue magnetic field, my palm points up, which is what the force does. And then finally, for the situation we kind of talked about before when there's an electron, right? So my thumb goes with the velocity, my fingers point into the magnetic field, and my palm would point up, but it's an electron, so it does the opposite, so it goes down. So here, give this a try here. Here we have a magnet making a magnetic field, and there's a positive proton moving through that field. Which is the direction of the force on the proton? All right, hopefully you got out of the screen. If we look at the actual proton itself, the magnetic field at this point is going to be tangent to the magnetic field line, so we point that way. And so my velocity, my thumb pointing up, the B field points to the left, and my palm is pointing out of the screen. And that's what we get. So now let's think about how this motion works. And so we're going to look at a case of a charged particle moving in a magnetic field. It's a very special case where the velocity is perpendicular to the magnetic field. And so if you do your right hand rule, put my thumb with the velocity, my fingers point into the page, my palm is going to point this way here. And so you'll note that the force and the velocity are 90 degrees to each other. And so let's imagine that this progresses a little bit, so the force might turn the velocity this way. If I do the right hand rule again, my force is still 90 degrees to the velocity, and it might pull it in, and you'll notice that if you keep doing this, that what happens is it moves in a circle with a radius r. And so whenever the force is perpendicular to the velocity, all right, you're always going to move in a circle, uniform circular motion. Another consequence is that the B field cannot do any work. Okay, so work is, remember you have to have the force has got to be either helping or hindering the motion. And here you're not increasing or decreasing the velocity. And so there's no change in the kinetic energy. So there's no change in the kinetic energy, the work has to be 0. We can calculate the R just by using, so we're essentially saying here F equals ma. Remember that A equals V squared over R. And so what we can do is for the actual force, we can plug in this equation here for the force. And we use the fact that this will be for the case when sine is equal to 90 degrees, right? Because we're talking about the case where V is perpendicular to the magnetic field. And if we solve for this, we get this equation here, which is mv over qb. So we're just using essentially some equations from 131 in combination with our new magnitude of the force on a charge in a magnetic field. And so here's an example. This is an old test question. So here we have, you have some situation where you're trying to, there's charged particles coming from some sort of an interaction. They're coming down this way, and you're trying to protect this green wall using a magnetic field. And so what you want to do is you want to deflect the particles. And so in this case here, you get the charge of Q, the mass of M, the velocity is this, and the magnetic field is this here. We know what kind of motion this is going to be because the velocity is perpendicular to the B field. So think about this and see what you can come up with. All right, so hopefully you're able to get this here. If not, let's talk about it. So basically the motion of the particles is going to be a semicircle like this here. Okay, it's going to basically go like this, and so you want to set it up so that the radius of that circle is exactly equal to this L. Okay, so basically you want it to be able, the particles to be able to turn completely around and not hit that green wall. And so if you set this up here with our numbers, you get about 0.28 meters, and so you say give yourself a little bit of wiggle room, and so that's 30 centimeters. And again, you can do the right hand rule here. As your particle's velocity is coming down, my thumb goes down, my fingers point into the screen, and the force would press out this way here. And that's what it does, and that's why you know that it circles that way as opposed to the other way. Now, we just looked at the case where the velocity was perpendicular to the B, but what happens is in general, you might have velocity that's perpendicular and a velocity that's parallel. Remember, the velocity that's parallel is not affected. And so in that case, if you have both velocities, your perpendicular velocity will cause you to move in a circle, and your parallel will just keep going parallel to the B field, and you get this helical path. Okay, so this is sort of the more general path that a charged particle will take in a magnetic field. So we talked about the force on a charged particle, so it's QVB sine of theta, and we use the right hand rule. So here, if my thumb goes with the velocity and my fingers point with those arrows, my palm is out of the page. Well, we have a very similar, I mean, if you have a charged current moving through a wire, it's exactly the same thing. It's just that it's acting on a bunch of different charges at once. And so what we do here is we take our equation, QVB, and so here I'm taking QVB and I'm multiplying and dividing by T, so I'm not changing anything, and then I put the one T on the bottom here. Okay, Q divided by T is the current, and then over here velocity times time gives us the length, okay, so how long this current is acting over. And so we can rewrite this equation, it's really the same equation, as ILB, and use the same right hand rule to figure the direction of the force on the current. So it's basically the same physics behind it. And here's an example. We have a wire that's hanging out in space. It's in a magnetic field. Gravity is acting down. I want to know, is it possible for this wire to be held up because of the force of the magnetic field? And if so, which way would the current have to go? Give us a try. All right, hopefully you got left to right. If I look at the case over here, if my current is going this way here, then what I do is I take my right hand rule, and if I take my right hand rule with the current, because the current is the velocity of the charges, so if my thumb goes with the current, it goes to the right, my fingers point into the page, and my palm would then give us a force that's moving upwards. And so you could set this up so that the force from the magnetic field was able to balance the force of gravity. Right, and finally we're just going to talk about how magnets and magnetic materials work a little bit. So Knight talks about this, but just real briefly, so all magnetic fields are created by moving charges. Okay, so we've seen a bunch of examples. We've seen that if you have a current, it causes a magnetic field. Well, basically all magnetism comes from moving charges. And so here's an example. If you have an atom, if you have an electron, okay, going around the atom, it's basically, it's a little current. And so what you have here is you have a little magnetic dipole. We talked about this last section, a little magnetic dipole. And so this is where the moving charge is. Now, in reality, this is true, but in reality, in most atoms, there's a whole bunch. Here I have a whole bunch of sort of electrons moving around, and so this effect tends to cancel out. All right, and actually what's the stronger effect is what's called the spin of the electron. And you've probably heard about this in chemistry class or maybe in an older physics class somewhere. But all electrons have what's called spin. And in a very general sense, we sort of imagine that the electron is rotating about its axis. Okay, so the electron has a negative charge. It rotates about its axis, and this is what we call the spin. Now, in reality, spin is something different than this, and you can't actually explain spin in terms that make sense classically or mechanically. It's a quantum mechanical effect, all right? But it basically has the same effect as if the charge was spinning. And what it really does is if you're a charged particle spinning around, you're a little microscopic magnet. So each electron is a little tiny magnet. Now, in most atoms, if you know anything about chemistry, each energy level is filled with spins, and they're in opposite directions. So if it's a filled energy level, or a filled energy level, basically those two spins will cancel, and there is no net magnet there. Okay, the two dipole moments basically cancel out. All right, so what can happen though is in any atom that has basically one partially filled level, you have one extra electron and one extra little tiny magnet. Now, in general, like in this picture here, these magnets are kind of just misaligned, so they don't do anything. But in some materials, like iron, okay, these magnets tend to line up. And so we call these kind of materials ferromagnetic. And ferro is just a word that means like iron. And so a general piece of iron that's just sort of hanging out will look like this here, and it has what's called magnetic domains. And so these are little regions where basically like right here, the spins tend to line up, so it's a magnetic field going down. Here they tend to line up, so it's a magnetic field going to the right. But what happens is if I put an external magnetic field from something else here, these domains will tend to line up with that magnetic field. And here's an example of this. So here I have a piece of iron on the right here, so a piece of iron or something that's ferromagnetic, and here I have a solenoid. And so the solenoid is set up, and so that this is like the north and this is the south. All right, and so what it does is it's a magnetic field makes these domains line up like so, and so this little magnet is basically kind of like this iron then becomes a magnet. It's like north and south, and basically this is making each little extra electron line up with the magnetic field. And so since this is a magnet with a south pole here and this one's like a north pole here, they attract. And so this is how magnets are able to pick up pieces of iron like paper clips. And pennies, for instance, don't work that way. They are not a ferromagnetic material.